So now in this lesson, let's discuss Cahn-Ingold rules of assigning R and S stereochemistry. Now think of a wheel. Think of a wheel. So let's say this is our original wheel, your steering wheel of your car. It goes into the dashboard. So we're going to call that group 4. Group 4 must always be away before assigning the final RS configuration, absolute configuration. If you're turning to your left, okay, then that left turn going this way is going to be judged to be an S because it's counterclockwise. However, if you're turning to your right, if you're turning the vehicle to the right, okay, so maybe you get to go to the right, you're doing a right turn, that's said to be R, and that because it's a clockwise rotation. In Cahn-Ingold rules, we assign R and S based on atomic numbers of atoms attached directly to the chiral carbon. So we are going to prioritize atoms or groups of atoms on chiral carbons based on their atomic numbers. So for example, let's look at this molecule that we looked at earlier. We looked at this molecule saying that that carbon in the center is really chiral. So what is the RS assignment of that? If you look at the periodic table, Br has higher atomic number than Cl than oxygen. So we expect the Br to get priority number 1, followed by chlorine. Br atomic number is 35, chlorine is 17. Oxygen directly bonded to the said carbon is having an atomic number of 8, that gets a 3. Hydrogen will be the baby. And we always want the baby to be away before we give our final absolute configuration, which is R or S. So currently we are going 1, 2, 3, and if you look carefully, we are going towards the left. So it's going towards the left, and that happens to be an S. Okay, so don't be happy and assign the S yet. Make sure the smallest group is away. It's away, so we keep the S. Now to get the stereoisomer of this, I'll just switch two groups. I'll switch the bromine and the hydrogen and do the same process. So this time I'll put the hydrogen on towards me and I'll put bromine away. That's how you get stereoisomers quickly, by just switching two groups. Again, bromine with high atomic number gets 1. Hydrogen with the least atomic number gets 4. Chlorine has atomic number of 17, it will get a 2. Oxygen has atomic number 8, it's going to get a 3 based on Cahn-Ingold rules. So the carbon in the center here needs to be assigned ROS. So if I follow the numbers, just look at 1, 2, and 3 for now. If I follow the numbers, they're still going S, which is counterclockwise. S stands for sinister, R stands for rectus. Still going counterclockwise, so we say S. But the smallest group here is towards us. That's a problem. Now, if for whichever reason you have the smallest group towards you and you have your temporary assignment, switch the temporary assignment from S to R or R to S. In this case, we have S. That S is going to be switched to the final assignment R because the smallest group is towards us. That is a shortcut we use to assign the correct absolute configuration if the smallest group is towards us. Okay. if the smallest group is on the plane, we'll need to rotate. So let's do that case. So let's use the same molecule, but this time around, I will put the smallest group on the plane, meaning a regular line. So if the smallest group is on the plane, I don't want the OH, I need the H. If the smallest group is on the plane, right, this straight line is on the plane, is right on your screen, flat on your screen. Put chlorine here. Let me put OH here. I'm switching H and OH. So what will be the configuration of this guy? If you want to assign such, what I usually do, I look for the other on the plane bond, and I will rotate along that on the plane bond in a way to put my H on the dash. So it seems to me that this hydrogen has to go to the dash here, and the bromine has to go to the OH, and the OH has to go to the H. I'm rotating this way along the other on the plane bond. Just always look for the other on the plane bond and rotate it. So what you are doing by hand, we are rotating 3 fingers. Okay, so we are rotating, I'm rotating my arm, that's the Cl. I'm rotating 3 fingers, whichever way. How will I show it on camera? I'm rotating 3 fingers. Okay, so the 3 fingers are H, OH, and bromine. I'm keeping the chlorine where she is, so I'll put the chlorine here. Now the H goes where the bromine was, the OH goes where the H was, and then the Br goes where the OH was. Now you see I've kept my 4th group away. So now my 4th group is away. So let's see, bromine again is atomic number is higher than that of chlorine. Chlorine's atomic number is higher than that of oxygen. So if I assign priorities 1, 2, and 3, I'm going S. With my smallest group away, I keep the S. So really, if I call this A, B, and C, A and C have the same configuration, same absolute configuration of S. So these are actually the same molecule. They are the same. They have the same configuration. But if I compare B and C, one is R, the other one is an S. We call them enantiomers. They are mirror images. There's no internal planar symmetry. They are non-super impossible. We'll talk about that later. We'll discuss those relationship, stereoisomerism relationship later. But here we are just assigning RNS. So I've shown you on a simple molecule. Let's do on a more complex molecule. Now, suppose you are given a structure that looks like this. A structure that looks like that. I can tell that there's a CH3 here. There's a CH3 there. The 2 asymmetric carbons that have 4 different things connected to them, I can definitely see that my asymmetric carbons are this. There's an implied hydrogen there. That makes this carbon to have 4 different groups. You will say, how do I know that? Well, you see that we have a CH3, we have a Cl, we have a hydrogen directly attached to this carbon, and then the rest of the molecules so different from the other 3, CH3, H, and Cl. Okay, so that is chiral. The other chiral structure is this one right here. You have a CH3, you have an ethyl, and then you have the rest of the molecule. So that carbon is chiral. Remember, there's a hydrogen. So those are the 2 chiral positions that we have on that structure. We will need to assign RNS to those 2 chiral structures. Okay, so follow me closely. So we will have to do it stepwise. Let's start with the first carbon here. What is the RS assignment of that carbon? So allow me just to redraw it, and then I'm going to show the hydrogen. Remember, this is a CH3. On this carbon, the highest priority is definitely going to be a chlorine, and the lowest priority will be a carbon, would be the hydrogen. Now we have to decide between this carbon and the CH3, who gets 2, who gets 3, between this carbon and this carbon. So to do that, I'll bring down this carbon, the CH3-1. Let me bring him down here, rewrite him, and I see he's connected to hydrogens. Not going back to the asterisk carbon. Okay, and then I'll bring this one here. We are trying to find a tie break. I see that he is bonded to a carbon, and then he's also bonded to hydrogen and hydrogen. So I'll write CHH. There's a tie break. Okay, since there's a tie break, I tell myself the yellow carbon is gonna get a 2, and then the CH3 will get a 3. So just focusing on this chiral carbon, I have 1, 2, and 3. 1, 2, and 3, and that's going left. If it's going left, it's temporarily an S. Is the smallest group away? Yes, it is. So we keep the S. So this position is originally an S. Okay. Now we do the same thing for the other asymmetric carbon. So I will redraw the molecule for clarity. We already know that the first one is an S. We need to assign this. There is a CH3, there is a hydrogen. So who gets priority in numbering? I would definitely say hydrogen gets number 4. And if you're to compare the rest, there will be a lot of work to do this. But I can tell you that the CH3 will have number 3. Why? This will be number 3 because it's only connected to hydrogens. This carbon is only connected to hydrogen, but this is connected to a carbon. This is connected to a carbon. So that will be 3. We will need now to determine who is going to be higher priority, the blue or the yellow. So I'm going to rewrite the blue here, and then I'm going to rewrite the yellow here. So the yellow and the blue seems to be connected to the same thing. You see the blue is connected to a carbon, this carbon, okay, and the yellow is also connected to a carbon. Of course, that carbon extends further to hydrogens. This is connected to a carbon, this carbon. So that's not helping us. So the best way to rank them is by looking at because these are the same. You see how they're the same? So we cannot judge from there. We are following the trail to decide who wins. So I will not rank them using the immediate carbons. Instead, I'll rank them using the carbon, the connections on the carbon after. So I will leave this process here, and then I will want to rank the blue based on that carbon, and I'll want to rank the yellow based on the carbon after. Okay, because we determined they're connected to carbon and carbon anyway, so we have to move one step ahead. All right, so the blue, this one is bonded to a Cl before it's bonded to a carbon based on atomic number, and then to a hydrogen. We are writing what's bonded to that carbon by decreasing atomic number. The yellow is definitely just bonded to HHH. Okay. Remember, both of them are CH2s, so we couldn't rank them. So we had to go one step forward. So we are ranking their extremities. All right, so there's a tie break here. This one wins. So in that case, because that one wins, we're going to give this one a 1, and then this one will be a 2. Remember, the methyl group is a 3 because he's connected to hydrogens. This carbon is connected to HHH. So initially, this is connected to a carbon, that's connected to a carbon. So the blue was connected to a carbon at least, right? This one, this carbon. The yellow is connected to a carbon at least. So you see these two will win over the CH3. So CH3 gets priority number 3. Then we've decided who wins between the two CH2s. We determine the blue will be 1, this will be 2, based on the work down here. So we are going 1, 2, 3. Okay, and that is going towards the left side. It's supposed to be an S. The smallest group is away, we keep the S. So this carbon right here is also an S. Now, if you are asked to name the molecule, including the RS configuration of this complex molecule, what you'll do, you'll know this is an S and that's an S. Find the longest carbon chain like you would in alkenes, giving the chlorine or the substrate the least number possible. It's a hexane, parent name. But since we have chirality at 2 and at 4, the name will be 2S, 4S, in parentheses, and then the chlorine is on the second carbon, 2-chloro, and then we have a methyl group on the fourth carbon, so 4-methyl, and then the parent chain name, hexane. So that's the complete name of this structure, including absolute configurations. Quite some work, right? But you need to practice. Okay? If you are given a Fischer projection? How would you assign chirality? So here we're going to do chirality, absolute configuration of a Fischer projection. So someone has given you this drawing. What would be the chirality? So what you want to do is to look for the chiral center, a carbon connected to 4 different things. So I see that this carbon right here is the only asymmetric carbon. Why? Because if you look closely, he's connected to a OH, it's connected to a CH3, which is different from the OH, it's connected to a hydrogen, and then the rest of the structure. So that carbon is the only asymmetric carbon, or only chiral carbon. This is not. It's connected to 2 hydrogens. This is not connected to 3 identical hydrogens. So let's assign the chirality of that carbon and eventually assign the chirality of this Fischer projection. So we have a CH3, we have a H, of course we have HH and another CH3. Overall, this molecule is chiral because there's no way you can carry it into equal half. So along this chiral carbon, hydrogen gets to a number 4 with atomic number 1, oxygen wins, and then we have to decide between the CH3 and the lower part who wins. So again, we do the extended process. Let that be the CH3 is connected to 3 hydrogens, writing the atoms connected to the carbon in decreasing atomic number. And then what about this carbon right here? So I'll put this carbon here. He is connected to a carbon, this carbon, before he is connected to the 2 hydrogens. So we have a tie break. This one wins because that carbon has a higher atomic number than the hydrogen. That is what we call a tie break. And we'll see that this carbon, the blue carbon here, is going to get priority number 2. The CH will going to get priority number 3. So this gets 2, this gets 3. And our numbers are going 1, 2, and 3. It seems like we are going to the left. That is temporarily an S. But remember, when you're talking Fischer projections, the horizontal lines are always wedges. That's a rule. The horizontal lines are bow ties. So this keeps our fourth group on towards us. So when it's towards us, it's an S. So if it were away, looking at the molecule from the back of your screen, it's supposed to be an R. So we will switch the S to the R. That's the shortcut I told you. When the smallest group is towards you, just switch the temporary assignment to the opposite. So if it was an R, I'll give it an answer of an S. Because it's an S, I'm giving it an R. So this is R. Now, if you're asked to name this molecule, including configuration, I have 1, 2, 3, 4 carbons with an OH. It's definitely a butanol. The butanol has an alcohol on the second carbon, so 2-butanol, but it's also an R configuration in parentheses. Someone else will call this R-butan, 2-ol. Okay, sometimes they'll ask you to name the chiral structure. Practice, 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 practice is gonna make perfect. Give the chirality the absolute configuration on this carbon. So remember, the C triple bond O is taken to be bonded to, that carbon is taken to be bonded to 3 other oxygens. In theory, C double bond O is taken to be bonded to 2 other oxygens. So by default, I can tell myself that C triple bond O has higher priority than C double bond O, right? However, let's come back here. Hydrogen has the least atomic number, oxygen has the highest atomic number compared to this carbon and this carbon. So this again, this carbon is taken to be bonded to 3 oxygens, while this carbon is taken to be bonded to 2 oxygens. So you can already tell yourself that the one bonded to more will win. By the way, there's a hydrogen here. Forgot to show it because it's an aldehyde. So you get a tie break. You're going to get a tie break here because this hydrogen is also bonded to the said carbon. So this gets 2 and this gets 3. So you go 1, 2, and 3. And that tells you that you have what? What you have here is an R. Do we keep it? Yes, because the smallest group is away. So this is our configuration. Okay, that's one quick example concerning multiple bond orders. So let's say you have, this time you have this. Okay, versus this. Versus the hydrogen. So this is connected to 4 different things. Again, this is priority 4 and this is priority 1 based on atomic numbers of what's connected directly to the said chiral carbon. We're trying to assign absolute RS configuration. Now, if you look at this, that carbon is bonded doubly to a nitrogen. We pretend that it's bonded to 2 nitrogens. While this one will, in theory, pretend it's bonded to 3 nitrogens. So this is bonded to 2 nitrogens and a hydrogen. The other one is going to be bonded to 3 nitrogens. Again, you have a tie break. So let me mark this with an asterisk so you know it's this one right here I'm ranking. So we have a tie break right here and it's all smiles. So it wins, and because it wins, the chirality on this carbon will have to follow the following numbers. So this gets a 2, that gets a 3. So you have 1, 2, and 3. And in this way, we are going S. Do we keep the S? That's the temporary assignment. Remember, you will only give the final configuration if you determine that this is away. Since it's away, yes, this has an S configuration. So when you have higher bond orders, remember to think of it in theory that carbon is bonded to multiple of elements, triply or doubly bonded to it. Okay, name these chiral structures using RS configuration. Let's work on this complex molecule right here. I can tell that this carbon right here is chiral. So is this. So we'll need to assign R and S for all this. So is this one right here having an implied hydrogen. So we want to determine the RS configuration on the 3 chiral carbons. Redrawing it here. So let's start with the first one. So let's start by working on the isopropyl chiral carbon, which is the carbon down here. So we need to decide who wins. I know there's a hydrogen. That hydrogen is gonna be the least priority with the least atomic number attached on this carbon. So I'll put the white here, okay, and then I'll go on the bromine side. Let me give him a blue. This carbon right here, let me redraw it here. He is bonded to a bromine, a hydrogen, and a carbon. So I'll start by writing the bromine, then the carbon, then the hydrogen. For the white one, it's gonna be a carbon, and a hydrogen. Already the blue one is winning because there's a tie break. See, there's a tie break right there. So this one wins right now, but let me test the other side. This side, I'm going to give him a yellow. It's bonded to hydrogen, and a carbon. So I'll bring him here. So it's firstly bonded to the carbon with the high atomic number, then HH. Still, the bromine wins. Still, the bromine wins. So the blue carbon here will get a 1. Okay, and then the hydrogen gets a 4. Then we will look between these two, who is winning. Between the white and the yellow, who is winning? I see there's a tie break here. The white is winning because carbon has higher atomic number than the hydrogen. Up here is CC, you cannot compare, so compare C and H. So the white is winning, and we are going to give him number 2, priority number 2, and then the yellow will get priority number 3. So on the isopropyl carbon, on this carbon, we are going 1, 2, 3. The hydrogen is 4. Okay, so that tells me I'm going clockwise, and the smallest group is towards me. See, it's towards me, so the correct answer must be an S, not R. When the smallest group 4 is towards you, switch the temporary configuration. So this is an S. Now we go to the next carbon. It's a lot of work, I know, but when you practice, it's enjoyable. So now let's look at the bromine asymmetric carbon. So we need to assign this guy. Okay, I can already tell that bromine wins with the highest atomic number, hydrogen loses. And then now I have to decide between this carbon and, let's say, the blue carbon. Who wins? Who gets number 1? Who gets number 2? Who gets number 3? Okay, so let me clean up a little bit. The blue carbon has 2 implied hydrogens. There they are. So if I bring this one here, he is bonded to a carbon, then to the 2 hydrogens. He is bonded to this carbon, then the 2 hydrogens, based on decreasing atomic numbers. And then if I bring the white one here, the white is bonded to 2 carbons, this carbon and this carbon, and then he also has a hydrogen. So I'll write CCH. We have a tie break. The white wins. The white wins because carbon has higher atomic number than hydrogen. So this is going to get priority number 2, and then the blue is going to get priority number 3. Okay. This number 4 here is for the hydrogen. This is for the hydrogen. Okay. So if I'm to follow the numbers on the bromine chiral carbon, they are going 1, 2, 3 in space. I think we are going R. The smallest group is at the back, so I keep it. So this one we will have an R configuration. We are not done. We need to continue with the mess. We need to assign the chirality of the last chiral carbon with the methyl group. If you practice, this process does not take time. I'm only taking time here because I'm showing you, I'm teaching you, but it's quite fast if you practice. You get used to it. So in this case, hydrogen will get 4. Hydrogen gets 4 because he has the least atomic number. And then by now you can tell that the CH3 will get a 3. Why? Because I showed you earlier that this carbon right here is taken to be bonded to 3 hydrogens. If you are to compare that with this carbon is bonded to another carbon, so it wins, right? It will win because at least this carbon is bonded to at least 1 carbon. The CH3 is now bonded to another carbon moving forward. We are not considering the carbon marked with an asterisk. We are moving forward with the structure connections. So CH3 gets 3, and then this CH2 right here also wins over the CH3 because at least it's bonded to another carbon. So the question is, between the CH2 in yellow and the CH2 in blue, who wins? Since right now they are same, we will have to rank what's connected after them. So we'll move forward here. I'm going to bring this carbon. That's the carbon. I see he's bonded to a carbon. Okay. Then 2 hydrogens in decreasing atomic number. But for this guy, if I bring him down here, remember I could not rank the circled ones because they are similar. So I move 1 step ahead in the bond. Follow the trail. This one is bonded to a bromine. Then it's bonded to a carbon. There is an implied hydrogen here. So I can write it down here. You see there's a tie break. So this carbon right here wins. And since he's winning, we're going to give that carbon priority. And what's the priority? Priority given to that carbon will be priority number 1. And then the blue one is going to get priority number 2. Now to simplify the structure, you'll see that we have the methyl group has 3, the hydrogen, which is definitely away. The hydrogen, which is definitely away, is going to get a 4, and that means that And that means that this one, based on our numberings here, remember we have a bromine here that helped us to make this carbon win. That means that this carbon gets a 1 and this gets a 2, based on what we worked here. Okay. So you'll see that the numbers are going 1, 2, and 3. So we're going clockwise. The smallest group is away. We keep the R. So this one will get an R. And we keep it here. Now, if you have to number this molecule or to name this molecule the conventional way, you'll find that the best numbering giving substituents priority will be 1, 2, 3, 4, 5, 6. Okay, the substituents should be given the highest priority. So that's the best numbering. This right here is an isopropyl. This right here is a bromo. And this right here is a methyl. So to name this molecule based on RS convention, the molecule will be named following alphabet rule. The molecule will be named 1s. You start by giving the absolute configuration 1s, 2r, 4r. That's where the absolute configurations are. Then it will follow by the bromo. Where's the bromo? It's on the second carbon, right? B comes before I. Then 1 isopropyl, and it's on the one that we have an S. Then allow me just to stretch down here. Then you have 4-methyl. It's a long name. The methyl group is on the 4th carbon. That's where we have our R, 4R. And then it's a ring, so we'll call it cyclo of 6 carbons, cyclohexane. So that's how you can name this structure including RNS. If you get such a question, you better work and be accurate. Check what you're doing, make sure you're doing the right thing.